Hello and welcome to this lesson on limiting reactants. In today's lesson, we will start by introducing the concept of limiting reactants in chemical reactions. Then we will look to understand how to identify the limiting reactant in a given reaction scenario. So far, we've covered the conservation of mass, the mole, and various chemical calculations. You are now familiar with how mass is conserved in chemical reactions. The concept of the mole as a unit to count particles in chemistry, and how to perform chemical calculations to balance equations and determine quantities. Building on this foundation, today's lesson will advance our chemical understanding by introducing the concept of limiting reactants. This is a crucial step because it helps explain why reactions stop when certain reactants are used up, even if others are still available. By learning how to identify the limiting reactant, we can predict how much product will be formed and better understand the efficiency and completeness of chemical reactions. Let's dive into the concept of limiting reactants and how to identify them in a chemical reaction. In almost every chemical reaction, we mix two or more substances called reactants to form products. However, these reactants are not always used up completely at the same time. One of them is often in excess, ensuring that the other reactant is used up entirely. For example, imagine you are baking cookies. You might have plenty of flour, known as excess, but only a certain number of eggs. Once you run out of eggs, you can't make any more cookies, even if you still have flour left. In this case, eggs are the limiting reactant. In a chemical reaction, the excess reactant is the one that remains after the reaction has gone to completion. The limiting reactant is the one that is completely consumed first. This reactant limits the amount of product that can be formed because once it's used up, the reaction stops. The limiting reactant is crucial because it determines the maximum amount of product that can be formed in the reaction. To optimize a reaction and make efficient use of resources, it's essential to identify the limiting reactant. To determine the limiting reactant, we compare the stoichiometric ratios of the reactants in the balanced chemical equation to the actual amounts we have. This is best illustrated with an example. Suppose we have the following reaction, and we start with 1 mole of N2 and 4 moles of H2, which N2 or H2 is the limiting reactant in this case. Step 1 is to identify the mole ratio from the balanced equation. The ratio of N2 to H2 is 1:3. Step 2 is to calculate how many moles of H2 are required for the given amount of N2. For 1 mole of N2, you need 1 times 3, which equals 3 moles of H2. Step 3 is to compare the required moles to the available moles to identify which reactant will run out first. This is your limiting reactant. We have 4 moles of H2, but we only need 3 moles to react completely with the 1 mole of N2 available. This leaves 1 extra mole of H2 remaining. This indicates that H2 is in excess whilst N2 is limiting. This understanding helps explain why reactions stop even when some reactants are left over. Let's dive into some GCSE level questions to apply our understanding of limiting reactants in chemical reactions. Question 1. Consider the reaction between hydrogen and oxygen to form water. The balanced equation is as follows. If you start with 3 moles of H2 and 1 mole of O2, which is the limiting reactant? First, let's identify the mole ratio from the balanced equation. The ratio of H2 to O2 is 2:1. Next, calculate how many moles of O2 are required for the given amount of H2. For 3 moles of H2, you need 3 divided by 2, which is 1.5 moles of O2. Now we can compare the required moles to the available moles. You only have 1 mole of O2, but you need 1.5 moles. Finally, we can determine the limiting reactant. Since you do not have enough O2 to react with all the H2, O2 is the limiting reactant. Question 2. Consider the reaction between magnesium and hydrochloric acid to form magnesium chloride and hydrogen gas. The balanced equation is as follows. If you start with 24 grams of magnesium and 73 grams of hydrochloric acid, which is the limiting reactant, first convert the masses to moles. For the moles of magnesium, we divide 24 grams by 24 grams per mole, which equals 1 mole. For the moles of hydrochloric acid, we divide 73 grams by 36.5 grams per mole, which equals 2 moles. Next, identify the mole ratio from the balanced equation. The ratio of magnesium to hydrochloric acid is 1:2. Now we can compare the mole ratio with the available moles. You have 1 mole of magnesium and 2 moles of hydrochloric acid, which matches the required ratio. In this case, there is no limiting reactant because the reactants are in the exact ratio needed for the reaction. Both reactants will be completely used up. Question 3. For the reaction between nitrogen and hydrogen to form ammonia, the balanced equation is as follows. If you start with 10 moles of nitrogen and 20 moles of hydrogen, which is the limiting reactant, what is the maximum amount of ammonia that can be produced? First, identify the mole ratio from the balanced equation. The ratio of nitrogen to hydrogen is 1:3. Next, calculate how many moles of hydrogen are required for the given amount of nitrogen. For 10 moles of nitrogen, you need 10 times 3, which equals 30 moles of hydrogen. Now, compare the required moles to the available moles. You have 20 moles of hydrogen, but you need 30 moles. Since you do not have enough hydrogen to react with all the nitrogen, hydrogen is the limiting reactant. Having found the limiting reactant, we can move on to finding the maximum amount of ammonia produced. We know the limiting reactant is hydrogen, of which we have 20 moles. Now we can identify the mole ratio between the limiting reactant and the product. The ratio of hydrogen to ammonia is 3:2. Next, calculate the number of moles of product produced. Since we are limited by hydrogen, the maximum amount of product is produced when all hydrogen has been used up. This means that we have all 20 moles of hydrogen reacting. Using the ratio, this gives that the number of moles of ammonia is 20 multiplied by 2/3, which gives us approximately 13.33 moles. By working through these examples, you can see how to identify the limiting reactant in various scenarios. This involves understanding the mole ratios from the balanced chemical equation, converting masses to moles when necessary, and comparing the required moles to the available moles of each reactant. In today's lesson, we delved into the concept of limiting reactants in chemical reactions. We began by understanding that in a chemical reaction, reactants are consumed to form products, but sometimes one reactant is used up before the others. We discussed how to identify the limiting reactant using molar ratios. By determining which reactant is in short supply, we can predict the maximum amount of product that can be produced. We then applied our knowledge to various reaction scenarios. By mastering the identification of limiting reactants, you can better predict the outcomes of chemical reactions, optimize the amounts of reactants used, and minimize waste. This concept is fundamental in both academic studies and practical applications in the chemical industry.